Hello everyone, my name is Alexander Kurth. I'm a PhD student in the Design and Computation group at MIT, advised by Professor Larry Sass. And this project is a collaboration with Professor Caitlin Mueller of the Digital Structures group at MIT and Tim Brodesser, the head of R&D for Twente Additive Manufacturing. Given that this is a shell conference and many of my fellow participants share an interest in 3D printing buildings, I have to begin with an obvious question. What about the roof? Every few months, a new 3D printed house or pavilion appears, and so far, without fail, they are missing the one key element that makes shelter functional. Instead of printed roofs, we see metal, glass, or in the case of the most recent full-scale print I worked on with emerging objects, giant pink balloons. The world is full of incredible spanning structures, including many made with masonry, a mode of construction whose logic is readily transferable to additive manufacturing. So why aren't we actually printing them? In this project, I will detail some of the challenges and solutions to the elusive roof problem through the lens of the squinch vault, a construction technique whose origins are likely too old and humble for us to place precisely. Beyond being beautiful structures, these are efficient forms that offer the potential to reduce waste and climate impact by engaging local materials and local material knowledge. The challenge lies in creating material-driven technology that is adaptable to a wide range of locally sourced materials, construction techniques, and the rapidly changing environmental conditions of our world. Here, we present a method for the translation of one type of masonry logic, the squinch vault, into a simulated, optimized, and then validated 3D printed shell. This methodology is widely applicable to more complex shell geometries and is flexible with regards to both material and mechanical system, accounting for detailed material and machine properties. My inquiry into this work began at UC Berkeley in 2018, printing small-scale Nubian vaults in clay, inspired by the drawings and projects of Nadir Khalili, Hassan Fatih, and more recently John Oxendorf. I was fortunate to then have the opportunity to teach a graduate course in which students explored ideas around 3D printed housing with local materials. We expanded the vocabulary of printable form, investigating optimum angles and limits of printing roof structures without centering or other formwork. We found that not only could we apply masonry logic to additive manufacturing processes, but that we could begin to work with more complex geometry, larger scales, and locally sourced earthen materials. Ultimately, a great deal of formal and functional freedom was possible at both the macro scale of the overall shell and the micro scale of interlocking toolpaths to change structural properties, wall thickness, and/or surface shading. This Nubian or angled vault work builds on the now classic contour crafting research of Barak Kashnevis, where this idea was initially rendered in 2004. Exciting research in concrete is also being produced in France by Carnot, Motamedi, and their numerous collaborators. Further exploration of this idea requires increasingly sophisticated toolpath characterization, a clear barrier to making these techniques accessible to both industry and individual builders. Fortunately, in the last few years, we have seen a number of well-validated simulation techniques for 3D printed concrete, which can be calibrated to material properties and curing or drying times of other materials like earth. Now that we can understand layer-to-layer dynamics in a relatively complex form, a whole range of possibilities opens up. So, getting into the details of our vault toolpathing workflow, we begin with material and machine inputs. These are things like curing time, strength, build area, printer speed, extrusion rates, and more. Then we introduce geometry, in this case, a very simple square plan. We use the force density method to then generate an optimal shell geometry, which remains fixed as we move into toolpathing. The path itself is parameterized such that they can be adjusted layer by layer in response to an additive simulation of the printed shell, which accounts for the aforementioned material and mechanical properties. From this point, we can feed displacement and information like overall path length into a multi-objective function, which in turn allows us to cycle through our design space in search of an optimized shell toolpath. The real advantage of this approach is that from the start, we are accounting for the key parameters which make a material printable on a given machine. In this case, we were fortunate to collaborate with Twente Additive Manufacturing, one of the leading large-scale printing and additive machine building companies in the world. With their machine and material properties, we were able to remotely generate models which printed well and were calibrated to their 9-axis gantry system. The optimization algorithm used here minimizes maximum displacement layer to layer with the option to weight overall toolpath length as a metric for print path efficiency. This model was driven by a set of constrained variables. These variables controlled spacing layer to layer at every point in the shell, allowing us to create non-planar paths that balance structural performance and a continuous printable toolpath. To make an efficient optimization model, this operation was done through a set of parameterized 2D curves which are projected onto the form-found shell. The result is a toolpath constructed in response to a layer-by-layer simulation of the printed geometry. This version assumes a constant shell thickness. Critical to accurate simulation is a robust and consistent meshing algorithm. The results of the optimization show that our optimal result is on a Pareto front and that the non-planar interpolated path generally outperforms all planar paths, including those with variable optimized layer spacing. During printing, we used variable machine speed to maintain even shell thickness across varying non-planar layer spacing. We tested 6-axis printer configurations, keeping the nozzle tangent to the shell during printing, though quickly found that this offers little apparent advantage to 3-axis approaches at this scale, which may be a promising finding for industry where we see a lot of 3-axis gantry systems. Printing the top segment of the vault requires the nozzle to be perpendicular to the shell geometry in order to avoid collision and failure at the end of the print. Here is one of the later tests running smoothly at a high speed in a 3-axis configuration. Here we see a finished shell. It's worth noting that the load test this print was designed for is its own self-weight. So what we see here is actually a print which has passed its own in situ load testing. A few final notes on the result of the optimization. We see a progressively lower layer spacing as slope decreases in the shell. This makes sense, given that the tighter spacing allows for a greater overlap between layers. This is very necessary at the top of the print where you have a very low slope. We also see toolpaths trending towards perpendicular relative to the flow of forces in the shell, where the load is highest. This gives us some insight into why this works. Looking to future work, we're hoping to expand the geometric vocabulary that we're working with here, maybe asymmetrical shapes, shapes with more sides. We're also hoping to validate a wider range of materials, especially earth. And hopefully, we'd like to build overall shell geometry into the optimization loop of the toolpath generator. Please reach out if you would like to discuss the work further or collaborate. You can reach me at my email, kurth@mit.edu. Thank you.